Okay, welcome to class meeting 12 of EECE574, the graduate level probability and random processes. Homework 6 will be assigned as usual, and there is midterm coming, and it's scheduled on this date, but I haven't yet decided whether it will be changed to a take-home exam or not. So you must be well prepared to take a three-hour exam, okay? Handout for the chapter 5, which will be covered today, is updated around 10 minutes ago, so you'd better download from the class homepage. Last time I talked about what to do as a graduate student. So if you view yourself as an apprentice in the medieval Europe, then it's much easier to understand what is going on in the graduate school. So you have your master and you have a lot of senior and junior apprentices. And apprentices usually do not directly do serious research. They usually equip themselves with new tools. So they are given empty toolboxes, and during the period of apprenticeship, they fill up the toolbox with useful tools. And the tools, you cannot get acquainted with every possible tools. So usually the master teaches you the fundamental tools. From those tools, some other set of tools can be easily studied, easily understood. So that is one of the important notion. And when you practice your tools, I told you there is a theory on a good practice. Of course, there are many theories, but one of the necessary conditions is like this, because practice usually requires iteration. And as an engineering student, probably you remember iterative optimization algorithm. So what do? First, you set up an optimization problem, which means that you have an objective function to maximize or minimize. So that corresponds to the first F. So focus. You want to improve what? And then you perform single practice and get a feedback. When you get a feedback, there are several things, but one of the most important things is, of course, the objective function evaluated at your performance. And then if you have a coach or you have a mirror, you self-coach it, anyway, you get some feedback. It's like, what about doing this? What about not doing this in the next iteration or next practice? Then what you do is you immediately, that is very important, you immediately get the feedback and try next iteration. So you try to fix it. That is one of the most important things. Got it? Okay, here goes the overview. Eventually, we have reached the chapter 5, which is a kind of a mixture of the graduate and undergraduate level probability and random processes. We have many important topics which we will cover and then move to this topic. Actually, some of the topics of the chapter 7 of the graduate textbook written by Populis will be covered in the second last sections of this chapter. Let's review. Last time, we learned what is the definition of the IID, random variables. First, the abbreviation IID is what? Independent and identically distributed. So you'd better divide it into two parts, independent part and identically distributed part. So independent, identically distributed. Got it? If we have IIDness, we have something very interesting. We will see it again and again. Anyway, Next topic was a function of two random variables. The question was that the function of two random variables is a random variable. Got it? And given that, what we wanted to do was probably to find the CDF, PDF, and something like that. But we rather focus on some special cases. So general function will be covered actually in this chapter. So you have multiple random variables, you have a function or transformation, and you have possibly multiple variables as the output. But here, we just focused on three things. First one was denoted by S sub n, which was defined as the sum of multiple random variables, probably IID, but not necessarily. And then mean of n random variables, that is the arithmetic mean. And then here goes something strange, but let me just call it a standardized sum of random variables. So you have standardized version of the ith random variable, and then you sum up, and you divide it by the square root of the number of random variables. By doing that, if random variables are uncorrelated, which we will define actually today, but anyway, assume independent, then what does that mean? This means especially Z sub n has zero mean and unit variance. So in this sense, Z sub n can be called as a standardized mean, a sum of n random variables. Anyway, why these are so important? Because they are related with some limit theorems we are going to study soon. So the first thing is related with so-called the law of large numbers, simply called the LLN, the law of large numbers. And this one is related to the central limit theorem. Got it? And last time, we studied especially the central limit theorem. But be careful. Here goes a Venn diagram you'd better remember. We are going to study, I'd better not doing that. Let me draw something. So anyway, suppose we have a sequence of random variables. So countably infinite random variables. Sometimes we want to talk about the convergence of this sequence of random variables. In that case, we have usually 4 modes of convergence, 4 different definitions of convergence we are interested in. First one is the almost sure convergence, and second one is the convergence in the piecemeal. Here, P is, I remember, chosen as greater than 1. Okay. Actually, it can be just positive, I remember. But anyway, and then here goes the convergence in distribution. Probability. And then convergence in distribution. Last time, we talked about convergence in distribution, which is a kind of the biggest one. Suppose that we have some sets, then this implication means that this is the biggest set, right? So most loose definition we studied last time. So convergence of CDFs to a CDF. That is the convergence in distribution. So what does that mean? We have a CDF of x1, we have CDF of x2, and this CDF converges to some CDF of some CDF of a random variable. Then we say that this sequence converges to some random variable having this CDF. Got it? the central limit theorem is related to this convergence in distribution, especially this one, the target or the limit distribution is Gaussian. Then we call it a central limit theorem. So here, after the standardization and summation, we have, in some cases like IID case, we have the central limit theorem. The simplest case is, as we've seen, is the Gaussian approximation to binomial, which means that if we have n binomial random variables, then what happens? Of course, we need to specify the probability of occurrence P. Then what? We know that mu is NP and sigma square is NP, so-called Q, which is 1 minus P, as we've learned in high school math. So what we do is that we sum up and we subtract, and then we divide by the square root of this variance. And what happens? Now this becomes a zero mean unit variance random variable, right? Given binomial xi's, IID. And then the central limit theorem says that this converges to what? Gaussian zero mean, 0, 1. Zero mean unit variance Gaussian random variable. That is the simplest example of the central limit theorem, which is an example of one of the simplest example of the convergence in distribution. Of course, we have different approximation to binomial, and that was Poisson approximation to binomial. And this proof is also using the convergence in distribution. However, it's not a central limit theorem because it converges not to Gaussian, but to Poisson. Got it? So this is what we've studied last time. And here goes the preview. So in chapter 5, we are going to study the expectation-related definitions and their results given multiple random variables. Got it? So most of the basic ideas are extensions of what we learned in the operation on multiple random variables. Okay? On that chapter, for the operations on single random variable, we studied what? Expectation. Second, transformation. The same thing happens here. Okay. Okay, let me directly go to the note. So the situation is like this. We have a source that generates a random vector, x. And what does this mean? We have, for example, the joint PDF or joint CDF or joint PMF that governs how the elements of random variables are related. They are in general dependent random variables. And the first thing is this. Given x, we want to do some operation to find a vector valued a deterministic vector. And this operation is called expectation. Got it? So here, I prefer using underscore or underline to denote some vector quantity. Of course, here, mu would be a vector, right? But I prefer putting underline under x. Okay, so this is a strange notation, but I prefer this. So mu sub x vector means what they are going to compute, the expected value of random vector. Now, remember what was the expectation of a random variable? What was the expectation of a random variable? So, given a random variable z, right? Given a random variable z, the definition, one of the definitions was like this. And this expression could be interpreted as what? Expectation is always summation of the product. What product? Value times probability, right? Now, we have two random variables. And we may have some mapping, right? And then how can we obtain the expected value of z? That would be the simplest case. Last time it was addition, right? Now, using the definition, we can write like this. However, if you just recall that the expected value is the summation of value times probability, you may write in this way. So this value is some g sub I and probability of I, and this value is g of xi, yi, and this is probability of I some tilde, something like that. That is the motivation of the fundamental theorem of expectation. So this expected value of z now can be rewritten in this way, right? And then our convention says that we have the value times probability. So this becomes the value, g of xy, and here goes the joint probability density. Got it? So this is the fundamental theorem of expectation when we have multiple random variables and we want to compute the expected value of the function of the random variables. This can be easily generalized for n random variables case. So n random variables are mapped to a single scalar through function g. In that case, the expected value of this output is simply can be written this way using the joint density of the random variables x sub 1 up to x sub n. Now, let's go back to our simplest case, but without IIDness. So without IIDness, without IID assumption, let's compute the expected value of a weighted sum of random variables. They may be dependent. Be careful. They are not necessarily IID. Okay? They are not necessarily independent. Now, how can you compute the left-hand side and to show it's same as the right-hand side? There are two approaches. Actually, we've already seen the major theoretic proof. What was that? So expected value of sigma alpha I xi is actually what? The integration of sigma alpha I x sub I of s, right? Times what? dp of s. Here, what is s? So you have your underlying probability space. And this capital X is the sample space of your underlying probability space. And this S is what? The probability measure. Given the measure theoretic definition, it's simple because this is a Stieltjes integral. It's linear. So you have sigma over I, alpha I times and this simply becomes alpha I expected value of xi. Okay? So this is simple. You don't need to involve the notion of joint density. But in the undergraduate program, this major theoretic proof may confuse students more than clarify. So here goes the idea. So you have expectation of sigma alpha I xi. And our approach is to use the joint density because every expectation can be written as summation of the value times probability. So here goes the value xi, and here goes the probability density, which is the joint density of n random variables. Let me see. Yeah. dx1 up to dxn. Now, again, this is what? This is an integration. So if the mean exists, actually, of course, here, individual expectation must exist. Otherwise, we can't define the summation. But anyway, here, under some conditions, we can show that this is summation over I, alpha I times the integration of xi and density of random vector x and dx. By the way, I will use this notation, f sub vector x, random vector x of vector x, instead of this lengthy notation. So we have the same result. So whether the random variables are independent or not, linear, so expectation of a linear combination of random variables is the linear combination of expectations. Got it? So whenever you see some equation, try to verbalize the result. Do not try to memorize equation. You are good at it. However, you must have your verbalization of the expression. Actually, that triggers you to recall the important result when you confront some real world or engineering world problem. Okay? If you just memorize these kind of things, it's very difficult to fetch the result when you need it. Okay, here goes the simplest case. When function ignores all the random variables except the first one, then we have our old friend. Got it? Okay. Let's move on to a lot of definitions because now we have multiple random variables. First thing is, again, the joint moments, because in single random variable case, we had moments. First order, second order, third order, fourth order. And probably you remember I talked about the third order moment, the kurtosis, and the fifth order moment. What was that? What was the name? Yeah, I already began to forget it. Anyway, so since we have multiple random variables, it's confusing. So let's focus on two random variables first. Okay? So suppose we have possibly dependent random variables x and y, and then given the order, for example, 5, we have a lot of choices. N could be run from 0 to 5, and k could run from 5 to 0. Right? So we have 6 fifth order moments here. And this is the notation from the Peebles textbook, but it's not that popular, so try not to memorize it. But anyway, so suppose we want to have n plus kth moment, then we can easily rewrite it that way. So using the, for example, fundamental theorem of expectation, you can compute it as far as you have the joint density. This n plus k is called the order of the corresponding moment. So the second order moments of two random variables, x and y, are what? The variance, the second order moment of x and second order moment of y, and expectation of x times y, right? See that? What are these? expectation of x squared, expectation of x and y, expectation of y squared. We already know this, right? So let's call this one. And this is called the correlation between x and y, or of x and y. So in other words, this can be viewed as the correlation between x and x itself. And this is the correlation between y and y itself. So we love to use this R sub something to denote it's the correlation. And that is very standardized notation. So we may say this is Rxx, this is Rxy, and this is Ryx, Yy. By the way, from the commutativity of multiplication, Rxy equals Ryx when x and y are random variables. Got it? And here was some strange definition. This really confuses students, but when two random variables are satisfying this condition, what is that? Verbally, expectation of product is the product of expectations, right? So if this holds between x and y, it does not always hold, okay? Be careful. If this holds, then what? By definition, we are going to say that they are uncorrelated. And this is amazing, actually. See that? This is a single expectation, but involving joint PDF, for example, of x and y. But on the right-hand side, you have expectations that involves only marginal PDFs, right? If you rewrite these things using integrations, you can instantly see that it's improbable, unlikely in general case. So this is a very special case. Okay. By the way, what does this mean in the real world? So let me draw a figure. So here goes the x-axis and y-axis. Now you have a random source that generates x and y, and they are dependent. So you have, for example, some 2D scatter plots. Now your scatter plot is 2D, right? You have 2D scatter plot. Now, what do you want to do? In the left-hand side, for each dot realization, right? You compute the product. And then you compute the arithmetic average, right? So left-hand side has the product, the unit, that is the product of unit of x and product of the unit of y. Anyway, now, is it amazing that you just compute the average of the x values, and then you compute the average of y values, and then multiply to get that the left-hand side, right? It's highly unlikely. But that is quite interesting case, as we are going to see. So we define this strange case as what? Uncorrelated. So x and y are uncorrelated if something strange happens, like this, that involves expectations. By using the previous notation, and sometimes for the first order moments, I will going to use not only first order. Yeah, I will use several confusing notations. Sometimes I will use x upper bar to denote mu sub x. Okay, got it? Upper bar means mean. So this means mu sub y. So what does this mean? Correlation equals the product of means. So this is mean of the product equals product of the means. Exactly this. You replace left-hand side with notation. You replace the right-hand side with notations. Of course, expectation, this is also a notation. So the statistics, probability, random variables involves a lot of notations. That, I believe, is one of the difficulty if a student does not study very hard. I never saw a student who do good in probability and random processes without studying hard. I never saw. Anyway, here was something interesting. So this uncorrelatedness looks very unlikely in general case, but we have interesting thing. If two random variables are statistically independent, we know what does that mean. Simply, we remember what? The joint density factors, right? Then they are uncorrelated. How come? So let's show. So we start from the correlation, right? And what? By definition, it's a double integration, right? And the value times probability. This is just definition, but we have statistical independence. What does that mean? This joint density factors. So we have density of X times density of Y. And from our multivariate calculus, we know that this can be, this double integration can be written as a product of the single integration. That's why we have expectation of X times expectation of Y. So amazingly, if independent, then uncorrelated. Got it? So now let's go back to this case. Of course, if we have a scatter plot like this, then X and Y can never be independent. So let me give you some special case that looks like an independent case. So suppose you have some scatter plot like this. Okay? Then what? Now, as you see, due to the symmetry, the expected value of the product of X and Y coordination is likely to be the expectation of the X coordinates and expectation of Y coordinates multiplied, right? So something like this. So this lemma is very interesting. If independent, they are uncorrelated, okay? Which means that the correlation becomes the product of means. Now, unfortunately, the converse is not true. What does that mean? What is the converse? If then something. And if P, then Q. The converse is if Q, then P. So uncorrelatedness does not always mean independence. See that uncorrelatedness, by definition, only requires this single equality to hold. However, independence requires what? This joint density factors into the marginal densities. And that's huge, okay? So independence is much stronger. Okay. Now, whenever we have a conditional statement, we have a statement, then we not only consider converse or reverse, we also consider contrapositive. And one good thing is that the contrapositive is always true. So if correlated, then they are dependent, right? If correlated, they are dependent. So in order to check whether they are independent or not, we may use this definition. Because expectation, since it is motivated by the center of gravity, is usually much easier than easier to handle than the joint density. So we check whether the left-hand side and right-hand side are very close or not. And if they are not close enough, then we can definitely say that they are dependent. Got it? So it's a kind of necessary condition to be independent. The uncorrelatedness is necessary condition. So here goes a Venn diagram. Usually, whenever we have three things, so here, okay, before, let me use something more. Yeah, here goes the term causation, which is actually not that important in our course, but it's very important in the real world. Causation means that something is the cause of the effect. Okay, so you have cause and effect. 원인과 결과 in Korean. Okay, now suppose two random variables are correlated, or they are dependent. Much stronger, right? Then X is the cause of the effect Y. Always, you can say that the X is the cause and Y is the effect, or Y is the cause and X is the effect. You can't say that. That is very important. Many uneducated people, including a lot of press reporters, even politicians, they just do not know the difference between correlation and causation. Even some research papers, they make mistake. Or many research papers are intentionally misunderstood to sell some products. For example, suppose you find a very remote, some town in, for example, some Africa, or even in this Gyeongbuk area, and you find that those people who live there has much larger longevity. And they all do something peculiar, like, for example, they drink makgeolli every day, for example. And if you want to earn money, what do? You say that makgeolli increases longevity. Yeah. That is totally absurd, right? In order to have such a conclusion, scientific experiments are required. You have some control and you have to... Anyway, so correlation does not imply causation, but causation may imply correlation. Causation may not imply correlation, depending on the situation. Now, here goes another definition, orthogonal. This orthogonal is related to some geometric concept, right? So in geometry, especially in the Euclidean space, when we have two vectors, right? Then we have the angle between the two vectors. If this angle is pi over 2 or negative pi over 2, we say they are orthogonal. And this is kind of idea of geometry, but in our especially high school math, from the high school math, we try to have a kind of analytic geometry. Actually, it's not analytic geometry, but it's just coordinated geometry. So coordination is involved in geometry. So we have what? Something like this. So we define the inner product between two vectors. And this is defined as what? The magnitude of A and magnitude of B times cosine the angle. And as I told you, if orthogonal, then this is 0. And if this is 0, and they are non-zeros, then they are orthogonal. So this correlation equals, this inner product equals 0 is sometimes just called orthogonality, right? Now, same thing happens. We interpret the expectation of the product of two random variables as what? As inner product. Got it? In that case, we may call they are orthogonal. By the way, you may not love this definition. Why orthogonal? We can call it differently. Interestingly, this geometric interpretation rarely occurs in some estimation problem and force us to call this to orthogonality. Anyway, because we have exact parallel in this multivariate geometry. In orthogonal case, something is minimized. And in our statistical estimation, if this holds, something is minimized, like that. That's why we define this strange thing without telling you why this is called orthogonality. But anyway, so we have just introduced two new definitions between two random variables. First, in the last chapter, we had independence, right? So if we have a pair of random variables, so this is a set of all every possible pair of two random variables jointly distributed. First, there are the set of two random variables that are independent, and here uncorrelated, here orthogonal in general. However, as we've seen in this lemma, what happens? This uncorrelatedness includes the set of independent. So what happens? This one kind of grows and includes something like that. That's why I draw like this. Uncorrelatedness is here. Independence is inside. What about orthogonality? They usually have intersection between independence and uncorrelatedness. Got it? So this is the situation. And then you have much less confusion. By the way, this Venn diagram approach is useful up to 3 subsets. And actually, there is a trick to have the most general case for 4 subsets. And you may find it from the web search. So if you really want to plot exact 4 subset case, now you know there is well-established figure you can find from the web. Okay, from the 5, forget it. Okay, impossible to visualize in the 2 dimension. Anyway, by the way, here was something strange. If you have 2 zero-mean random variables, and they are orthogonal if and only if they are uncorrelated, how can you prove this? So here you have orthogonality, right? 2 random variables are orthogonal. And here you have the product of expectations. And they are zero-mean random variables, so they are 0. And now you have 0 equals 0, so uncorrelated. So what does this mean? Actually, you only need not 2, but at least 1 zero-mean random variable. Then orthogonality if and only if uncorrelatedness. So this is a special case of orthogonality and uncorrelatedness, okay, at the same time. Now you can define some mth order joint moment given n random variables, and a simple extension you have. So far, we just considered this product type joint moments, and here goes new definitions related to central moments. What does that mean by central? Central is related to subtracting the mean, okay? So if you have multiple random variables, now you consider subtracting means of each random variable. By the way, there is a very special, more special thing related to centralization is standardization. So centralization and standard means what? You do more than just centralizing the mean. You standardize. So you compute the z-score, okay? You subtract the mean and divide by its standard deviation. So these central moments are all actually related to the standardized moments. Anyway, the definition of joint central moment is just simple. You need to subtract the mean. So we first start from the two random variables case and generalize very simply. Especially when these powers are 1, we call this central moment the covariance between x and y. So here, the covariance is translated in Korean, 공분산. Here, 공 means co, and variance is 분산, right? So, unlike the correlation, you have the product after centralization. Got it? And as we've already seen, there are 3 second-order central moments given 2 random variables. And this is the case where the exponents are 1 and 1. And if they are 2, 0 and 0, 2, you have your variance of x and variance of y back. Okay? So you have what? Second-order moments, second-order central moments, like sigma sub x squared, sigma sub y squared, and covariance of xy. So this is what? Cxx, Cyy. Of course, you can change the order to have the same value. So this notation is also very popular. Okay? Sometimes even people use sigma xy or sigma yx. Got it? Now, we can define the something parallel to uncorrelatedness independence, but since we have this simple equality, we don't need new definition. By the way, why this is true? Covariance equals correlation minus the product of means. Why? Can you show this? Actually, it's not that difficult. You just need to use the definition. So from the left-hand side, you have expectation of x minus mu x times y minus mu y. And then you expand the argument. Then you have xy, x mu y, mu xy plus mu x mu y. Then what? These are sum of random variables. So you can write it as sum of expectations. So you have Rxy, and then what? What is this one? Expectation of x times mu y. Mu y goes out, so you have mu x mu y, mu x mu y plus mu x mu y. So you have 2 terms canceled. That's why you have covariance equals correlation minus the product of the means. By the way, sometimes you really got confused about this minus sign, but it's very easy to remember. This is centralized version. So anyway, you need to centralize your uncentralized version. That's why you have negative sign here, okay? Minus sign here. Anyway, now let's view this one. Does it involve something familiar? Yes. If uncorrelated, what happens? Uncorrelated means that expectation of product becomes product of expectations, means equals 0. So actually, uncorrelatedness means covariance is 0, if and only. Okay? So uncorrelated means 0 covariance. Okay? Be careful. I'm not talking about independence. Of course, if they are independent, then they are uncorrelated. So they have 0 covariance. So if the x and y are either independent or uncorrelated, then covariance is 0. By the way, what if they are orthogonal? Remember, orthogonality talks about what? This is 0. This inner product looking like an inner product is 0. So covariance, so this is 0 means that covariance is simply the negative of the product of the means. Got it? Similarly, if an xy are orthogonal and either x1 or y has mean 0, then covariance is also 0. Now, here goes the most important thing. The Pearson or without Pearson, the correlation coefficient between x and y. And probably you've seen a lot of definitions, but I myself really loves this definition. Because as I told you, it's what? It's related to the standardized versions of x and y. Okay. So what is the unit of this one? No unit. What is the unit of this term? No unit. So the product has no unit. So first thing you have to remember is that the correlation coefficient between x and y is a unitless quantity. That is the first thing. Okay. And now let's try to rewrite this one. Then what happens? So the denominators are constants, so they can be taken out. So this is sigma x, which is the square root of sigma x squared. And this is sigma y, which is the positive, of course, square root of sigma y squared. So you have what? Square root of the variance of x and variance of y. Okay? You just translate. And what about the numerator? That is the product of centralized versions of x and y, which is what? The covariance. So correlation coefficient now can be rewritten as what? In terms of all central second order centralized moments. The numerator has exponent 1, 1. Denominator has exponent 1, 0, 2, 0, and 0, 2. Be careful. I told you that the correlation coefficient is a unitless quantity. What about unit of the numerator? Unit of x and unit of y. What about the unit of variance of x? Unit of x squared. So that's why you need square root, okay? So never forget that. If you just compare the units, you can avoid a lot of mistakes. Now, I do not like this one. But anyway, by the way, sometimes this correlation coefficient between x and y is simply denoted by rho xy. Okay, it's not rho x comma y, rho xy. Of course, you can write it rho x comma y, but people just love to not to have a comma here. Now, here goes some interesting thing you've learned probably in statistics course or undergraduate probability. This correlation coefficient, the unitless quantity, is always between -1 and 1, possibly equality can hold. Okay? And the first question is why? Why this boundedness of the correlation coefficient happens? And second, what does this mean with equalities? And the simplest proof goes like this. See that? You have expectation of what? Something squared. Then your result is always non-negative, right? Expectation of something squared is sigma something squared times its probability. Something squared is non-negative, probability is non-negative, so non-negative, right? And now let's take a look at something which to be squared. That is what? Some variable a, real number in this case, times z square of x plus z square of y. And you may say that, what? Why should I have to consider this one? Actually, the reason is simple, because this is the simplest way to prove. Okay? But anyway, so what is the left-hand side now? Left-hand side, you can show that becomes a quadratic function of A, real variable A. And this is always greater than or equal to 0 for all A. Does it sound familiar to you? Yes. From your middle school math, whenever you see something like this, you use what? That big D or D/4, right? What is the name of that in Korean? 판별식. What is that in English? Discriminant. Okay. So you use the discriminant, and what? The discriminant is negative or 0. If you do that, you will see the correlation coefficient is always in between negative and positive 1. Got it? So that is first, the proof. Second, what happens if you have equality? So let's substitute plus 1 and no, not in A, but in that discriminant. What does that mean usually? That discriminant equals to 0 when you have what? When you have this equality, right? What would that mean? You have some random variable, this is random variable, squared, and its expectation equals what? Equals what? Equals 0. What does that mean? Expectation of some random variable squared equals 0. What does that mean? This is what? Sigma value times probability, and that is 0. What does that mean? This is 0, okay, with probability 1. So probability of Z equals 0 is 1. And I told you, we call this as what? Z is 0 almost surely. Okay, so Z is 0 with probability 1. Okay, Z equals 0 with probability 1 or almost surely. That is our official terminology. By the way, when rho equals 1, this A becomes, I remember, yeah, rho xy, that's what I remember, okay? And rho xy is 1, so what do you have? You have, just a second, something strange. Yeah. Okay, got it. So this is 1, okay? Rho equals 1 means A equals 1. Rho equals negative 1 means A equals negative 1. So you have something strange. See that? This is 0 with A equals 1. What does that mean? Is it? Just a second. Yeah, I believe the sign must be changed. So if rho equals 1, then A equals negative 1. Okay. And rho equals negative 1, A equals positive 1, something like that. So if I remember correctly, in this case, we have y minus mu y divided by sigma y equals x minus mu x divided by sigma x. So this is rho equals 1. What does that mean? In both cases, we have something like this, right? Y is what? Y is an affine function of x with probability 1, right? So if you know x, you exactly know y. Of course, in many cases, this is called linear relation, even though it's an affine relation. Okay, people really love linear, even though it's not linear. Okay, so in order to fully understand this proof, actually, you have to start from the general approximation first, affine approximation first. So you consider approximating y using some y hat, which is an affine function of x. You start from this one. And you consider the mean squared error. So y minus y hat, which is mx plus n. M is slope, n is the, what is that? The abscissa or something. Yeah, intercept, y-intercept. And then you minimize this one with respect to m and n. And you will see that even though this has two variables, you can minimize this one with respect to n first. And then you will suddenly see that after you substitute optimal n, you will see that this minimization can be reduced to this minimization. Okay? So it's like this one appears in the second step of this minimization. First, you find optimal n, and then you substitute it and try to minimize m. Then you have this one. Actually, this m corresponds to sigma x, a divided by sigma x. So eventually, what you see is that in general case, this mean squared error can be rewritten this way. So you have found the m, right? So here in this case, no, something's wrong. Okay, okay. Let me use. Okay, I found what is wrong. Let me just subtract. Okay. Then everything's okay. Yeah, I will correct it. Okay. Then what happens? You can show this one becomes this value. Here, the mean squared error is what? Upper bounded by the variance of y. Suppose you don't do anything, then this m becomes this term, so mean of y. So this is simply variance of y. And if you have some correlation between x and y, actually you can reduce the mean squared error. So your affine approximation can be better if they are more correlated. What if they are perfectly correlated? Means rho xy equals 1 or 0. Amazingly, if you substitute 1 or -1 here, the variance becomes 0. What does that mean? Actually, this means that if you plot the 2D scatter plot, you have this, right? Or some straight line with different slopes. One thing interesting is like this. Take a look at this one. So here you take the this variable and equate them, and you have that one. Okay, and this is what your best affine approximation of y equals mean of y plus correction term. Got it? And that correction term is related to the standardized value of x scaled by sigma of y multiplied by the correlation coefficient. Now let's take a look at the unit of this. Unit of y, unit of y, unit of y. See that? Unit of x, unitless quantity. Got it? And now we know that the standard deviations are defined as positive square root of variances. So this is positive. We assume sigma x and sigma y are positive values. Now, the sign of rho xy. So rho ranges from -1 to +1. And if they are positive, what happens? Our best linear approximation has positive slope. Got it? Be careful. Rho xy equals 1 may still mean slope different from 1. Rho equals 1 means that no error from the affine approximation. Rho less than 1, greater than 0 means that best affine approximation has positive slope. Got it? If we have a negative correlation coefficient, then our best approximation is negative. By the way, if you take a look at this one, you can easily see that when you have some general scatter plot, then you have the mean of x comma mean of y, say this one. Interesting thing is this. Interesting is that the best affine approximation always crosses this point. Okay? Because of this reason. And here goes some stupid guys' mistakes. Probably you remember there has been a lot of academic manipulation of research papers, especially those who do experiments. Okay, they move some points in their scatter plot and show some very nice looking curve and try to become a PhD. But they are stupid, so they do not know that when they have linear affine approximation, their curve, their affine function must intersect mean of x comma mean of y. So when people try to verify, first the necessary condition when they have affine approximation is that they just find the mean of x, find the mean of y of the dots, and check whether that mu x comma mu y is crossed by the best linear approximation. Actually, similar thing you can do for quadratic approximation, exponential approximation, whenever you invoke something like mean squared error minimization. So there are stupid guys, okay? Never be friends with them. Anyway, so equality holds if and only if y is an affine function of x. Very interesting. And here goes what I exactly told you. Okay, see that the slope is negative, and there are dispersion, right? Means rho cannot be -1, but less than 0. Here, no deviation from affine approximation, and slope is negative. Rho is -1. Here we have the exact opposite. And here we have positive correlation coefficient. And here we have 0. But be careful. Rho equals 0 means what? The numerator is 0 and numerator is the covariance. What does that mean? Correlation coefficient equals 0 means uncorrelated. However, uncorrelatedness may be obtained with very strange scatter plots. Suppose you have 1, 2, 3, 4, 5, 6, 7 scatter plots. They all have 0 correlation coefficient. But definitely you see the dependence, right? You see the dependence. What does that mean? Dependence means that when you condition on x, the conditional PDF of y must not depend on value of x. But here, if you have value of x, the scatter plots, the 1D scatter plots look like that. And if you change x, they are dependent. Here, again, they are dependent, right? Again, dependent, right? So these 7 cases show all dependent random variables n, x, and y that have 0 correlation coefficient, uncorrelated case. Got it? So I repeatedly say, be careful when you interpret correlation coefficient, when you just talk about second order moments. Okay, now, so far I just said that the warning. Here goes something very familiar. Variance of weighted sum of random variables equals weighted sum of variances, but this weight is squared now. When they are uncorrelated. Now let's show why this is true. So let's start from the left-hand side. So we have variance of sigma alpha I xi, which may be said y. What is the variance? What is the variance? It's the expectation of centralized version of the random variable squared. And then what happens? Here goes the most important trick. You use centralized version like this. And this is squared. And how many terms do you have when you have n random variables? N squared terms. So these are I, j, alpha j, expectation of xi mu I times xj mu j, right? Now, what if the random variables are all uncorrelated? What does that mean? This equals 0 when I is not equal to j, which means that if we assume uncorrelatedness, we have what? N terms only. Here we have n squared terms, right? If uncorrelated mutually, right? So pairwise uncorrelated means that we have single, sorry, x means that we have square and variance of xi. This is this. Now, what if we have all alpha i's equal to the unity? Then 1 squared equals 1. That's why in our even elementary school statistics, what? Variance of summation equals summation of variance. Be careful. We need to square the weights. The reason why we didn't do that in our probably 6th grade elementary school, right? Because the weight was 1. Never forget that. Now, here goes joint characteristic function. And joint characteristic function, of course, the definition starts from the simplest 2 random variables case. And in 2 random variables case, what we use is the analogy of our characteristic function as the Fourier transform of the actually reversed PDF. So suppose you are a signal processing student. You know what is Fourier transform when you have a single signal, right? Or that signal is one-dimensional signal, which means that that is a function of, for example, x, right? Now you have a function, but of 2 parameters, x and y. What do you do? 2-dimensional Fourier transform. So this is nothing but 2-dimensional Fourier transform, but with this signs flipped, right? Sometimes these are called symplectic Fourier transform, but forget it, okay? Anyway, so this is 2D Fourier transform. That's it, okay? Now, we want to have very simplified notation because we want to generalize this to n-dimensional case. So here goes the case. So this is the generalized version. So we have n random variables. And then we have what? Here, of course, we have n tuple, n times folded integration, e to the j omega 1 x1 plus omega n xn times the joint density, which is simply written as x in r to the n, e to the j, omega vector transpose x vector times the density of x vector dx vector. Okay? So we are strongly motivated to introduce this notation. The joint characteristic function is denoted by capital Phi of random vector x of vector variable omega. Got it? And as we've seen in 2D PDF, in order to marginalize, what did you do? We integrated. Same thing happens. Okay. So from this relation, so this is the 2D inverse Fourier transform, right? You can find the marginal characteristic functions by simply marginalizing it. But in this case, you don't integrate. You just substitute 0. Okay. Then you can drop the other variable. Okay. From joint moments, joint characteristic function, you can obtain joint moments because characteristic function can generate moments unless it does not exist. So as far as the joint moment exists, you should be able to find it from the joint characteristic function. Now here goes some important lemmas. And let me finish by talking about this one because they are so important. See that here in this lemma, you have n random variables, they are independent. And I'm asking you the joint characteristic function. So how many variables do you have? N variables, right? And these n variables can be shown that the joint characteristic function has this form, product of individual characteristic functions evaluated at omega sub I. So this is called prod, similar to sigma, and this means multiplication, as you know. And see that you have n variables. Now, here goes some looking very similar thing, but be careful. In the subscript, you have summation of independent random variables, which is a single random variable, right? This is what? This is a single random variable. You may say this is y. So in this lemma, you are asked to compute a characteristic function of a single random variable. Unlike the previous lemma, where you are asked to compute the joint characteristic function of n random variables. So you have a single omega here. And then after using independence, you have here very similar looking result. But be careful, you have what? Single omega here. And I'm asking you to work on this one, derive these two results yourself, okay? And you will learn a lot. Okay, that's all for the day. See you next week.